Now I want to talk about a very important topic in the field of theoretical computer science, and that's the Church-Turing thesis. So formally, it states that the language of Turing machines, namely the set of recursive languages, coincides with any set whose membership can be algorithmically decided. So in plain English, what does that mean? It basically means if you can solve a problem by constructing an algorithm to do it, then there exists some Turing machine that implements that algorithm. So any process that has some sort of decision procedure to check if it's a yes or no answer or whatever, there's always a Turing machine that can do it. So for example, there exists some Turing machine M, such that the language that M accepts is a set of all binary strings X, such that X is a prime number. For example, this language here. Such a machine would be particularly horrific and complicated to construct, but the point is we know it exists, because we know there exists some decision procedure that checks if X is prime. You just check all the factors below it and check all the numbers below it and see if anything divides it, right? So because there's a finite decision procedure, there's some sort of algorithm that can check if a number is prime, there certainly exists a Turing machine that checks if numbers are prime. Now for problems that are unrelated to binary numbers, like traveling salesman problem, or checking if a shape has the same area as another shape, or something like that, we can usually encode these objects also as a binary string, and then once again we can then feed that binary string to a Turing machine which can check the properties we look for. So we usually use this notation with left and right angle brackets to denote an encoding from a class of objects to binary strings. So for example, to encode a graph, we can represent each node as a string of ones separated by zeros, where the number of ones represents the nodes the other nodes that node can transition to. And then we separate all the nodes in the string with double zeros. So for example, I've got a graph G here. This is my graph G. It's got a bunch of vertices and a bunch of edges. I could encode this graph as this following string, which is denoted by angle brackets G. So this is vertex 1, which states I can go to vertex 2 or I can go to vertex 3. So V1 can go to V2 or V3, and then separated by double zero. V2 can only go to V1. That should be a single one by itself. Whoops. There we go. So V2 can only go to V1. V3 can go to V2 or V4, and V4 can go to V1 or back to itself. So that will be one such way to encode a graph as a Turing machine. The important thing to note, the important thing to care about is not the specific encoding itself, but just that such an encoding is possible. And then we can consider graph problems as Turing machine language recognition problems. So for example, does there exist a Turing machine M that recognizes the language of all encodings of graphs G, such that G is a connected graph? Well, if there's an algorithm check if a graph is connected, i.e. check from every vertex does there exist a path to every other vertex, and that means this language here can be recognized by some Turing machine, okay? So the encoding itself, the specific encoding is not important. What is important is that one exists, okay? In a similar fashion, we could encode Turing machines as binary strings. So here is one possible such encoding that I'll go through. So we're going to assume the states of the Turing machine are labeled Q1 through Qk. Q1 is always the starting state, and Q2 is the only accepting state. So you can always take a Turing machine with more than one accepting state and redraw it such that there is only one accepting state by taking all the accepting states, making a new accepting state, making these guys rejecting, and then making a free transition to the accepting state. You can always modify a Turing machine, rewrite it differently such it's only got one accepting state, and such that the start state and the accepting state are different. This doesn't weaken the Turing machine anyway. So we can make those assumptions. And we'll assume the tape symbols are encoded as x1 through xm, where x1 is always a 0, x2 is always a 1, and x3 is always the blank symbol, and then if there's other symbols, you can just pick other x's. And we'll refer to the directions left, right, and stay as d1, d2, and d3. Now I can take a single line from the transition function and encode it as a binary string in this manner. So when I see this binary string, I should read this as from state qi, reading symbol xj, transition to state qk, writing symbol xl, and moving the tapered in direction dm. So there's a direct correspondence between a single part of the transition function and a binary string. Now each of these indexes is at least 1, so this string contains no double ones. So I could encode an entire Turing machine as just encoding each step in each line in the transition function, and then separating them with double ones. Okay, so let's go through an example of that. Here's such a Turing machine. Here is its transition function. Let's encode it. So what was my rule for encoding? The zeros for the exponents separated by ones. So if I'm in state Q1, that's going to be a single 0 separated by a 1. I see a 0 that corresponds to x1, so I put a single 0. Transition to state Q3, so that's going to be 3 zeros. Write a 1 to the tape, a 1 is x2, so 2 zeros. And then move left, which is in D1, which is a single 0. So this string here encodes this line of the transition function, and then we can fill in the rest of this. And then we can take all these new strings we've got and concatenate them all together, separated by double ones, because none of these strings contain double ones. And just like that, now we've gotten a string here, binary string, that's encoding this Turing machine here. And once again, the actual way we do the encoding isn't terribly important, just that such an encoding exists. And here is one such encoding. Some methodical way to take a Turing machine and write it as a binary string, such that from the binary string I could recreate the Turing machine, right? Just by following the rules going backwards. So that is how we can encode a Turing machine. Why is that useful? Because now we can get, if we encode Turing machines as binary strings, then questions about Turing machines can be rephrased as language recognition problems. So Turing machines can ask questions about other Turing machines. So for example, I could have a Turing machine M, such that the language of that Turing machine is all encodings T of other Turing machines that have exactly 5 states, or the encoding of all Turing machines T that only accepts strings of the form 0 to the n, 1 to the n. So this here would be the language of all encodings of all Turing machines that only accept strings of this form. So any Turing machine in the world you can think of that accepts strings of this form, its encoding, its representation as a binary string will be in this set. Or we could have even more sort of meta problems where the language of M is all Turing machines T, such that the language of T is all strings, all elements of the set of all strings. So this is basically the set of all Turing machines that accept everything, right? So now we can have sort of meta problems, Turing machines talking about Turing machines. As a brief side note, we can also have a Turing machine that accepts multiple inputs by encoding many strings into one, using what's called prefix coding. So taking a tuple of n things, we can prefix code each one and then concatenate them together. So in this case, a prefix coding on x is a whole bunch of ones out the front, the number of ones being the length of x, and then a 0, and then the string x. So the idea being, if you concatenate strings together, you can uniquely break them apart again. So for example, if I have the string x1 as 101 and the string x2 as 0001, I can encode a tuple of these two things as this string here. So if we try to, 3 ones because x1 is of length 3, 0, 1, 0, 1. 4 ones, x2 is of length 4, 0, 0, 0, 0, 1. So for example, if I try to decode this string here, I just read from left to right. 1, 1, 0, okay, so the next 2 bits is x1. And then 1, 1, 1, 0, okay, so 3 bits. That's my x1, that's my x2. So the idea is I can uniquely decode a tuple of 2 things from a string. Why? Well, now I can encode machines and strings together. So now I can ask questions about both of these things. So for example, I could have a machine M, such that the language of M is the encodings of all tuples of M and W. That should really be like a tuple of the encoding of M and W, such that M accepts W. So this is the set of all tuples of Turing machines and strings, such that the Turing machine M accepts the string W. Or I could have, again, that should be the encoding of M. There we go, because M's a Turing machine. The language of M is all Turing machines M and W, such that M accepts W in exactly 10 Turing machine transitions. So the crux of this course is, the final question we want to ask is, are Turing machines infinitely powerful? Is there some language that even Turing machines can't recognize? Is there something even beyond the reach of Turing machines? So have a think about that, and then we'll get the answer in the next video.